So antenna impedance is actually combination of antenna resistance and antenna reactance, in fact. So let me term it as antenna reactance. Now moving further, so we can say that this RA is actually equal to the combination of R, which is the radiation resistance, and RL, which is the loss resistance, in fact. So this is how we talk about the antenna impedance, in fact. So let me write the whole equation. It becomes then ZA equal to RR plus RL plus JXA, where we know each and every term right now. RR is actually the radiation resistance and RL is actually the loss resistance, and JXA denotes the reactance of the antenna, in fact, which actually denotes the storage energy in antenna near field, in fact. So this shows the antenna storage energy in near field, in fact. Okay, now let's move further and let us derive some equations about it in order to know what kind of received power we are getting at the antenna terminals. Let this be A and B. So these are the antenna terminals, and the antenna impedance is actually that we are looking from here. This is actually the antenna impedance. So this point, in fact, and the whole from this point the load is actually starting. Okay. So in some cases what happens is that we have no transmission line, and let us assume that we do not have any transmission line. So in that case we are going to have VG and then obviously the ZG and then no transmission line, and then we have antenna attached directly without the transmission line. So let us see this case first, and then after looking at this case we will then go for other cases as well. So so the complete source and antenna impedances, source and antenna impedances, inserting all of them. So this gives us a diagram of like this. Let me draw it here. I also have a space over here, so I can go here as well. So it means that if I say, you will agree, if I say VG and then I say RG and then I say in series we have JXG. Okay, so this is actually my generator impedance, in fact, and then I have my current I flowing through the circuit, and then this here starts the antenna impedance, where this denotes RR and then this is RL, and in series we have JXA, which shows the antenna reactance, in fact. So, and this completes the circuit, in fact. So this portion is my antenna impedance, in fact. And now if you see, the voltage drop over here is VR and the voltage drop over here is VL, and the voltage drop over here obviously is Vx. If for example I denote it like Vx, and the current flowing through the whole circuit is I. So this shows a case where we do not have any transmission line, and we have antenna terminals A and B over here, and this is without the transmission line. So why we are considering at the moment this case, this is going to be very clear later on. So now let us go with the complex power associated with any element in equivalent circuit here given as in front of you. And so the power is actually equal to V RMS and I RMS, obviously the complex conjugate of it, so which is actually equal to half of the peak voltage multiplied with the peak current and complex conjugate of it. So this star actually shows the complex conjugate, in fact. So we are going to assume the peak values. We will assume peak values. So we will assume peak values of voltages and currents for all the impedances, the power calculations, the impedances, the power delivered and the power received. We are going to consider all of them as the peak values. So now the peak current for the simple series circuit in front of us right now can be written as I is actually equal to VG divided by obviously ZA plus ZG. So we have these two impedances, in fact. So I can also write it like this: VG divided by RG plus RR plus JXA. Or I can do what? I can combine all the RG plus RR plus RL, the resistive parts, and then plus JXG plus XA. So this can also be written in this way. Now the power radiated by the antenna may be written as the power radiated by antenna, let it be PR, and this is actually half VR into IR, the complex conjugate of it, and it can also be written as half IRR, where VR is the voltage associated with the radiation resistance. So I can also write it like this, and this equates to half I magnitude square RR. This equation shows the power radiated by antenna, and which is PR. Actually, the power radiated by the antenna is denoted by PR. So the power radiated, radiated by antenna, power radiated by the antenna, let us denote it by PR, as I discussed previously as well. So it may be written as PR is actually equal to half of VR and I steric. So, and then it can also obviously be written as IRR into I steric. So this in fact give us half of I magnitude square, in fact, when you multiply both of them, and then RR, where RR is actually the radiation excuse me, where RR is actually the radiation resistance, in fact. And this I magnitude can be written now as VG magnitude divided by divided by the magnitude of the resistances, which is the impedance, in fact, which is RG plus RR plus RL, in fact, and it is XG plus XA whole square, in fact. Okay, now this is how we represented the power radiated, and we can now plug in the value of I magnitude. By plugging the value of I magnitude in this equation, in fact, is going to give us the received power equal to, if you solve it a bit, it is going to give you VG magnitude square RR divided by 2 RG plus RR plus RL whole square plus XG plus XA whole square, in fact. So this is how it goes, and this equation in fact shows us the power radiated out of the antenna, power radiated in fact. The power dissipated in the antenna can also be easily found. So we can also find out the power dissipated, the power that is dissipated in as heat. So that can also be represented as PL, where L shows the loss, and it may be written as PL is actually equal to half of VL and I static, where static denotes the complex conjugate. So likewise it can also be written as half I magnitude square RL, in fact, now, because VL is actually can be written as I RL. So this gives us this equation. Now we already knew the value of I magnitude, so we can plug in the value of I magnitude and we can find out the power dissipated in the antenna, the equation for that. So it is, now by plugging in, you can find out easily, it is Vg square into RL. This time it is RL because it is loss resistance, and the same in the denominator, which is Rg plus RL plus RR square plus Xg plus XA whole square in multiplied with 2. So this equation actually shows the power dissipated in antenna, in fact, the power dissipated in antenna. So and the reactive and imaginary power can also be now so let me write the reactive power that is imaginary, what is the spelling of it? Imaginary component of the complex power stored, the reactive power stored in antenna, in fact, in the near field, antenna near field. So what is that going to be? So this can be denoted as Px, for example. So this Px is actually equal to half of Vx. So please remember that let me draw